say, please, everybody who's listening, go and check it out because it's really wonderful, and consider donating.
Yes.
Yes. And now I'm gonna go ahead talking about probabilistic programming, which is the topic of my PhD. So currently I'm a PhD student at Edinburgh, working with Andy Gordon and Charles Sutton. I will try to introduce you to probabilistic programming, to explain what that is, where we might want to use it, and what the problems are, what are the challenges. Let's start. So I'm going to begin with a very famous kind of puzzle, brain teaser, which perhaps a lot of you know. It's called the Monty Hall problem. I'm still going to summarize it very quickly. It goes like this. Imagine you're on a TV show, and there are 3 doors, and the idea is that you're going to choose one door, and there are prizes behind the doors, and you're promised to win whatever the final door you open has behind it. So let's like one of the doors has a fancy new sports car behind it, and which obviously that's what you want to win, right? Because it's fancy and new. And then the other 2 doors have goats behind it. And yeah, you're trying to pick the best price. So let's suppose that we picked door number 1. We selected door number 1. Now the host of the show, Monty Hall, will open one of the other 2 doors. But the rule here is that he's always going to open a door that has a goat behind it. And then he will present you with an opportunity. You can stay with the door you picked in the beginning, door number 1, or you can switch to the other door that hasn't been opened, door number 3. And the question is, should you stay or should you switch to door number 3? Again, perhaps a lot of you know this problem, but still I'm going to give a few seconds. Just think about this. Like, would you, if you were there playing this game, would you pick door number 1 or door number 3? Now, perhaps a little bit unintuitively, it turns out that your chances of winning the sports car are better if you switch to door number 3. So even though before we had the prizes behind the doors were evenly distributed, right? So we would have 33% chance of winning the car, no matter which door we choose. Now it turns out that there is a bigger chance of winning the car if we switch to door number 3. What's happening here? This is very weird. And to understand this, let's work through the maths. We're interested in the probability of the car being behind door number 3, right? So this is our initial setup. We selected door number 1. And that's a third. That really is a third. But this is not really the probability we're interested in. The probability we're interested in is the probability of the car being behind door number 3, given that Monty opened door number 2, which is a different probability. And we can use Bayes' rule to actually derive this probability by sort of flipping around the conditioning. So the probability of the car being behind door number 3, given Monty opens door number 2, is the probability that Monty opens door number 2, given that the car is behind door number 3. And we know that this is this probability is 1, right? Because we've chosen door number 1. The car is behind door number 3. So Monty has to open a door that has a goat behind it. So that must be door number 2. So that's 1. And multiply this by the probability that the car is behind door number 3, which, as we saw before, oops, oh no. As we saw before, that probability is a third, right? And then we divide by the probability, the total probability of Monty opening door number 2, which is sort of an average between the probabilities of him opening door number 2 under different selection and under the car being behind the different doors. And it turns out that this total probability is 2/3. So if we make this calculation. So yeah, so there are 2/3 chance that the car is behind door number 3, given that Monty opened door number 2. And what we did here is, so what's happening here is that this probability distribution, that is the probability over the positioning of the car, given what Monty did, is called a posterior distribution. That's what we're interested in. And what we did to derive this posterior distribution is called Bayesian inference. That's all that probabilistic programming is about. Probabilistic programming is about Bayesian inference. So it's a way of, it gives you a tool to describe your probabilistic process. In our case, this was this game where things are distributed randomly and so on. And gives you a way to describe this in terms of a program, and then sort of automatically does stuff for you. So there are two things that you need for a probabilistic program. One is the choosing randomly, and here we can see that this describes the Monty Hall problem. So we firstly chose the car randomly, the positioning of the car randomly from 1, 2, or 3. So the car is either behind door 1, behind door number 2, or door number 3. And then we pick one of the doors at random again. And then Monty picks one of the remaining doors such that the door doesn't have the car behind it. So we remove the door we picked and the door that has car behind it, and we randomly choose from there. But that's not enough to actually make this a probabilistic program. This really is a conventional program. You can implement this in Python. You can implement it in F#, right? You just need a random number generator to sample from, to generate randomly from a discrete distribution. What makes this program probabilistic is that we have we can have observations. So we can decide that we can kind of condition the program on some data. So here we say that we observed that we picked door number 1, and that we observed that Monty picked open door number 2. Now, probabilistic programming languages aim to having something like this. This, by the way, is pseudocode, so don't try to compare this to any existing probabilistic programming language. Having something like that, we want to invert the process, the generative process. So we described how we generate data, and we want to invert this generative process and figure out how our beliefs about variables in the program change. So again, we have two things. We have distributions over variables, so we have random variables in a probabilistic program, and we also have the opportunity to do Bayesian inference, which is this inversion. When we observe data, we can see how things change. And of course, this program is quite quite easy. It only has discrete variables, but we can have something more complicated. We can have continuous variables. For example, here we say that sigma is some variable generated from a gamma distribution, mu is a variable generated from a normal distribution, and then we say that y is an array of variables that were all generated from the same distribution, normal distribution, with mean mu and standard deviation sigma. And then we can observe the actual data, and the goal is to try and figure out how our beliefs about the standard deviation and the mean change based on the data. And both of these examples are really, I think we can, well, we worked out one of them analytically, right? We worked one of them on the slides, and I think we can work the other one too. But that's not always the case. In general, Bayesian inference is very hard. I'm not going to go into details how we do it in general, but we can't always, actually in most cases, we cannot out things analytically. We need to do some sort of approximation, and that's very difficult. So one thing that we definitely don't want to do is to do inference by ourselves. So that's where probabilistic programming comes in. We want to automate this. And here, perhaps you're thinking, oh, well, that's like we have data, we have some inputs and outputs and all that. And that sounds awfully like deep learning and all that kind of buzzy stuff. But it's different. It's a different thing. So this slide, I kind of compare conventional programming, probabilistic programming, differentiable programming, which is deep learning, really. And in conventional programming, we will typically have an input. So like imagine an easy conventional program. We have an input, we have a function that does something with this input. We provide both of those things, and we get an output, right? Easy. In differentiable programming, we have an input and an output, say images being mapped to is it a cat or a dog, and we're trying to work out the function that maps these two things together, the input and the output. In probabilistic programming, we have an output, we specify a random function, so something that involves random variables, and we want to figure out how the belief of other variables of the input x changes based on this output. And this is very important. It's a probability distribution. The probability distribution that we have on the on X. And this is why probabilistic programming is important. This is one of the advantages of probabilistic programming. Is that it quantifies uncertainty. So the fact that we have a probability distribution means that we can quantify uncertainty and we can give some sort of guarantee about how certain our estimates are or our predictions are, which is very valuable in some domains. It can also work with small amounts of data, like deep learning. And it separates, at least the dream is to separate modeling from inference. So we only think about this generative process, the forward generative process, which is much easier, especially can be targeted towards domain experts. So a domain expert can come and bring their domain knowledge that a statistician won't necessarily have by building a probabilistic program. And then the probabilistic program would automatically do inference, which should be for the statisticians to figure out in a way. Here are some examples that I personally find very exciting. So this is an example from a probabilistic programming language called Picture, where we our generative model, so our probabilistic program, describes how an image, a 2D image, is generated from a 3D face. So we have some sort of 3D model of a face. There can be different lighting, there can be different rotations of the face and so on. And we describe how an image is rendered from these settings. And then the actual inference bit is when we observed an image, we observed a 2D image, and we try to reconstruct the 3D model of the face. And then we can render it under different poses and different lightnings, like here, after we've reconstructed it. Another exciting example is, so I think probabilistic programming has been used a lot in different sciences, especially with STAN, which we're going to talk about in a bit, but not only. And this example I find very exciting because it has to do with particle physics, which is kind of cool. So in particle accelerators, like the Large Hadron Collider, what we're trying to do is, so we collide two particles, and then they decay, and they can do it in many different ways, and that's sort of random. So there are different possibilities that can happen there, and then we observe the decaying particles, and we want to see if our theories about physics hold based on this data. And this generative process, again, can be described with probabilistic programming. So we describe our theory, what we believe about physics, we observe the actual data, and see if there's a match. And my personal favorite is astrophysics. And here we have a similar thing where we have theories that describe how we believe the universe evolved, but we don't know that, right? They're just theories. All we know is what we see when we look in the sky. So all we have is a 2D projection of the sky around us. And this is what we observe. So we describe the generative process of rendering the sky around the Earth, and see if our theories make sense. Okay, and now something very topical, which is I decided to actually go and check how many papers and pieces of work there are in terms of coronavirus and probabilistic programming. And this is what happened. These are not all. So all of this is from the last few months. All of these are different, either papers, some of them are published, some of them not, some of them are just work in progress that has been published somewhere online, and so on. But all of this is probabilistic programming. A lot of them are using Stan. There are a few that use other languages. But yeah, this is what happens. So we see how because of this ability to quantify uncertainty with probabilistic programming and with general, it becomes really important when we're dealing with something where it matters if we make a mistake, right? So policymaking, healthcare are such domains. And right, so here I was supposed to say, oh, well, where's the catch? Why haven't we heard of probabilistic programming? But now I kind of rethink this because there are actually a lot of things mentioned here. But in any case, it's not, we don't solve every problem with it, right? Why can't we solve every problem with it, given that it sounds so great? Like we just input the output and decide what your input was. And the catch is that actually probabilistic programming has been around for a very long time. And you can see this is an outdated plot of a lot of probabilistic programming languages out there, very outdated. There are a lot new ones in the past few years that are not here. But all of them have kind of focused in one aspect of probabilistic programming and Bayesian inference on one class of models, or maybe one sort of inference algorithm that may be slow, and so on. You can see part of this in this diagram. So you see this this big section here, which says, oh, discrete random variables only. And we see this big section here that says bounded recursion only. And these are not all the restrictions that a probabilistic programming language might have. There is a very, very, very incomplete list of restrictions that a probabilistic programming language can have. So we have discrete variables only, or continuous variables only, or the likelihood might need to be differentiable, or inference might not be automatic, right? So in other words, if the dream, because Bayesian inference is so difficult, as I mentioned before, if the dream of probabilistic programming is for a language to be fast, general, so we can express a large class of models with it, and user-friendly, which includes being automatic, so that we don't have to do Bayesian inference ourselves, we live in the sad reality where we have to pick 2 out of 3. And we have to sacrifice in one direction in order to make this work. Or at least we definitely haven't figured out how to combine all 3 of those yet, so that we create a probabilistic programming language that is all 3 of those. And this brings me to my own research, which is about using techniques from the programming languages community to existing and applying them to existing probabilistic programming languages to hopefully improve the language in one of those aspects. So either improve the speed of inference or the usability or make the language more general. And today I'm going to talk about one of my projects that kind of demonstrates this and uses F sharp. Yeah, I hope that's interesting. All right, so the project I'm going to talk about is has to do with the probabilistic programming language Stan, which I mentioned already several times. So it's perhaps um, the the most widely used probabilistic programming language. It comes from Columbia University, from the statistics department there, but now it has developers and users and user groups all around the world, and it has very friendly and wonderful community. It's used a lot in the sciences in particular, and a lot in the statistics community. So it's now looking back at the triangle we had, Stan is fully automatic. It's an imperative, fully automatic language, as in it does Bayesian inference automatically. And it's very fast. So it uses Hamiltonian Monte Carlo, which is a fast inference algorithm. But it has sort of a unusual syntax, and also it restricts the class of models we can have. And here you see an example of a Stan program. This is similar to the program I showed before, the second program. So again, we have some sigma that comes from a gamma distribution, some mu that comes from a normal distribution, and then an array y that comes from a normal with mean mu and standard deviation sigma. And so that looks great. That looks very much like before. We have this probabilistic assignment here. That's the only unusual thing. But we also have these blocks. And it turns out these are actually not all the blocks in Stan. They can be up to 7 blocks in Stan. And each of them has a very particular purpose. It needs to appear they need to appear in order, and you need to put the right piece of code in the right block. And not only that, but sometimes you might get a less efficient program by reordering things. So let me go into a bit more depth here. Here, just understanding this problem, we can understand it generatively by saying, okay, so here we are given y, that's the data, right? We want a probability distribution over the parameters mu and sigma, given the data y. That's this bit. And then we specify this is the generative bit, right? We specify how we believe y was generated from mu and sigma. Then at the end we have this bit that is generated quantities where there might be other quantities that we're interested in that we can generate once we've done everything else. Just a short disclaimer, this is not the actual syntax you're going to use in the generated quantities in Stan, but for the simplicity of presentation, I decided to include it that way. Right, but why is this different to this? Why is it why is it separated? Well, the truth is we're actually interested in we're interested in this YSIM as well. So this YSIM is just it's sort of a simulation. We simulate from the parameters we inferred. So it's the same, as you can see, it's generated the same way as Y, but it's fake. We don't observe it. And we're interested in that. So really, we are interested in the probability of mu sigma and Y sim given Y. But why do we have to separate y in a in this block? It turns out the answer here is there's several answers to why we stat has these blocks, but for me the most important is efficiency. So we actually plug these blocks into different, when we compile to an inference algorithm, we plug these pieces of code in different places, and we use, in order to get the distribution over mu and sigma, we use one inference algorithm. And in order to get the distribution over y simulated, we use another inference algorithm. And it's because it's faster than if we had put y over here. But of course, this is not very friendly. It's not very user-friendly. And yes, there is a very good reason for it, but ideally we would like to remove it. And you might be thinking, oh, come on, like, I mean, it's not that bad, right? There are just like 4 blocks here. It's not that complicated. Well, let's see some real examples that demonstrate what I mean by these blocks being confusing. So I'm going to start by this example, which is it's a model that tries to predict who's going to win in the 2016 U.S. elections. So it's a bit outdated, but still, it was used to try to predict who's going to win back then. And so this is the STAMP program. It's like 177 lines, and you can see that it's the blocks are very big. The biggest block is transform parameters, whatever that means, instead of model, which you expect to be the biggest bit, because this is like the core where you say how your data was generated, right? I should probably increase the size. And also, it's sort of, it's confusing to read. So if you go here and you try to figure out what's happening, you'll see that all the variables pretty much come from standard normals. So this doesn't really tell you anything about how these variables are collected. And you see some weird names like alpha 01 that comes from normal 01. What is that? If you go and search for it, you see that actually this alpha 01 depends somehow on alpha, right? And alpha is, let's see. Oh no, maybe I didn't pick the right parameter because that's actually a parameter. Okay, well, sorry about that. I think I didn't pick the right parameter here. But what I'm trying to say is that sometimes you have things very far away from each other. For example, let's pick the other example because anyway, because that's one of the COVID models that I showed on one of the previous slides. So same thing, we have this very big, well, bigger in any case, transform data block, and actually it's so small only because we put a lot of this in a function in the functions block, which is separate. And if we go down, we will see that all the things that are involved in model, again, they come from standard normal in most cases. This is called gamma rho, and it implies that gamma comes from something. And this is just a comment, and this comment exists because this code is written by the wonderful Ben Goodrich, who is a Stan developer. And this is one of the good Stan practices to write these comments. But actually, gamma is what you're interested in, because if you go here, so if you go to transform parameters, so no, if you go to parameters, you see that gamma rho is a parameter. So supposedly that's what you're interested in, but actually you're not. You're interested in gamma, which is a transform parameter, and it's somewhere over here. And every time you want to change something, you have to go ahead and like find where this is defined and figure out which exactly is the parameter, which transform parameter, in what block you should put it. Anyway, I hope this shows how confusing it is, because even I'm confused. I am extremely confused right now. This is what the first project I worked on in terms of Stan had to do. So I worked on SlickStan, which is a language built on top of Stan, and it's a blockless version of Stan. So you can see that it has very similar syntax. Again, there's like deterministic and non-deterministic assignment, but no blocks. And it uses information flow analysis and type inference to translate this blockless Stan to Stan. And I'm not going to go into details, but if you're interested, you can see the F# Exchange talk from last year, which focused a little bit more on this. All I'm going to talk about in this talk is that I used F# for that, and why I think F# was a great choice to develop SlickStan in. So SlickStan is built in F#, and because I'm a PhD student and I work in the programming languages community, the papers we would submit in the programming languages community, syntax, if you create a new language, there has to be like very formal syntax and very formal set of rules that describe what happens with this language throughout the paper. So this is what the syntax would look like. I will say, oh, okay, and an expression in SlickStan can be this or that, right? It can be an array element or a function call. And again, with statements, it can be a sampling statement, it can be an assignment, it can be a sequence. And this is what these definitions look in F#. So this is the definition of expressions and statements of SlickStan in the compiler for SlickStan, which is exactly the same, right? It's like, oh, okay, so an expression can be a constant, it can be a variable, it can be an array, and so on. And not only that, but the code for different rules different formal rules that need to be present in the programming languages paper, such as these typing rules, also looks the same. So let me walk you through this. Might be familiar to a lot of people listening to this, but just in case, this is a typing rule which says that here gamma is a map from variables to types, so it's a typing environment. And this says, oh, well, x, the variable x, it's well typed in gamma if when we look x into gamma, we will get this type t, right? And here we have, oh, well, the constant c is well typed in gamma with this type if the primitive type of this constant is tau and this level, which again, I'm not going to go into this. This is part of the information flow, is data. And the F# code, once again, looks exactly like this rule. So, well, pretty much like this rule. So we have, if gamma contains that key, then do this, otherwise fail. All right, but just in the last 2 minutes, what you are probably the most interested in is how can I use probabilistic programming in F#? Well, there are several things that you can do. So one of them is you can use infer.net. So what I described here is a compiler written in F# for some other probabilistic programming language. But if you want to use probabilistic programming in your F# project, one thing that you can do is to use infer.net, which is a probabilistic programming language for .NET, which already exists. It's not very F#y, so, be prepared for that, but it's there. Now, another thing you can do is, and I hope will be done more fully soon, is an embedded approach. And actually, Evelina gave talk 2 years ago at the previous F# Conf about this, and well, she kind of presented a lightweight embedded probabilistic programming language in F#. And it's a very good talk. So if you're interested in this, go ahead and watch it. I strongly recommend it. And until we have something else, some other embedded probabilistic programming language, hopefully for F#, unfortunately, these are all the choices. So to wrap up, probabilistic programming languages are about automatically doing inference where we just provided data to some generative model. So we say, okay, this is my data generated from these parameters. How do my beliefs about the parameters change? Why do we want to use it? Because of easy interpretability. We actually write the model. We write our belief. It's not data hungry, and we can quantify uncertainty, which can be really, really important in some sectors. How? It's hard. There exist many probabilistic programming languages out there, but each makes certain sacrifices, and we don't have anything truly amazing yet, unfortunately. Thanks. If you have any questions, I'm going to be around to answer them.
Thank you for a great talk. I think you answered many of the questions that we were watching on YouTube with your last example of the computation expression, but some of the questions that people had were around sort of what would be the best way of using this in F#. So you mentioned that the computation expressions idea. I think one thing that I was sort of curious about is whether there's sort of probabilistic programming embedded in some other languages that you're aware of?
Yeah, many. So here, these logos. So this is Stan, which you can use in many. It's a standalone language, but it can be coded for many interfaces. So you can use it in Python. You can use it in I don't know, MATLAB, R, Julia. From the console, you can it has many languages it can be used for. This is Edward, which is built on top of TensorFlow. So this is again Python. This is Pyro, which is built on top of PyTorch, and this is again Python. There is Gen, which is built on top of Julia. And many others, many others. So there is plenty of probabilistic programming languages out there. I don't think a part of a part of Infer.net, there is anything else for F# currently, but hopefully that will, hopefully will change soon.
I think with all the excitement that people had from your talk, that will change very soon. That's a good call to action. So one other question I wanted to ask is, when you're describing the model, you sort of showed some code snippets, and I was wondering if the code you actually have to write to sort of express those models, if that actually ends up being more functional, or if it ends up being more sort of imperative with loops. How do people actually express those models?
Sorry, which model?
Well, I think even in Stan, when you're writing some model, are you going to be using things like recursion or loops?
So they mostly use loops and for loops in particular. So as you can see here, am I still screen sharing?
Yeah.
Yeah. So for loops, it's not. It's an imperative language, really. And I think there are probabilistic programming languages that would use recursion. They're much more functional. Like I think Anglican possibly is one of them. I'm not that familiar with them, so I can't really say. But the reason why for loops in particular, and that's for loops, not while loops, make sense for Stan, is because one of the constraints that Stan has is that it can't have, it has to have like a static size of random variables. So it can have random number of random variables. It can be a variable, as in it can be like a user provided variable of random variables, but it needs to stay constant during inference. So a recursion where we recurse on a random variable wouldn't make sense in Stan. We can't do it.
Thanks. And I think final question from YouTube is whether the Slick Stan project you're working on is available anywhere. Where should people go?
I got this question last time too, and I can't believe I still haven't made it available. Yes, it will be. It will be. I promise. It is not yet, but keep your eyes open.
We will.
We will tweet about it and have an announcement at F# Online.
Oh, thank you.
All right.